We will start, we will briefly recap what we did last time with a little extra things here and there. So, basic idea is that statistical mechanics has two parts. One is equilibrium statistical mechanics that addresses problems like phase transition and properties of matter, and then you have the time dependent statistical mechanics which addresses things like chemical kinetics, details of protein folding, that is the dynamics of protein folding and things like that. These are very complex systems, and as I tried to explain that there is a huge amount of work that gone into it. In chemistry, theoretical chemistry, when we do quantum, we really do not do quantum in any kind of sophisticated way. We do density functional theory and that kind of thing, nothing against it, because people who have developed them are physicists and they are very smart people. In statistical mechanics, however, starting with many people like Onsager, Kirkwood, Zwanzig and others, there is a considerable contribution that has gone in from chemistry, physical chemists. Of course, physical chemistry, as you know, was born essentially 1900 or 1901, around that, with the advent of Arrhenius and Ostwald. And what they did essentially was some form of other is the statistical mechanics. However, there is a history which I will recap again, but before that let me tell you what would be the first few things, the preliminaries we did last class. I will just do 5 minutes recap of that, because I like to put really hit on the head again and again on few points that I think important to the students, and I get very upset when they do not understand. Now, what I will do today, probability of statistics, then I will explain why we need to know some amount of very elementary, what you have learned by and large in your class 12, 11 or 12, and fundamental concepts. Actually what we will do here, something like phase space, trajectory, and then I will try to motivate and explain to you why this time dependent statistical mechanics, equilibrium and time dependent statistical mechanics needed these things. So, I hope to finish this today. So, the Liouville theorem and Liouville equation, we will do these things, and these will be next, not in this thing. Then we will go on. My very favorite and one of the most favorites is the fluctuations and response function. Then we will do, this is amazing, the ideal monatomic gas, but even the translation entropy is used almost every day in the drug discovery or drug DNA interaction, because that gives you the entropy of a drug going into DNA and the entropy it is losing, which is the Sackur-Tetrode equation. Then of course, here we have all the things that we need, rotational, vibrational entropy, things essential for chemical kinetics. We use them without knowing where they came from, but they came from a very elementary statistical mechanics. So, we will do that, and then we will do bit of quantum statistics. I am not too greatly fond of doing this thing, but there are some nice points here that I think students should know, and they are not taught and are not covered in books, very simple things. Then we will go to Ising model, which I think is one of the simple model, the first and perhaps the only solvable model of interacting systems, and one must know Ising model. And this is the A of the chronology and of my doing. Now, what I was briefly tell the hierarchy, the way things happened in statistical mechanics, the way it was evolved, it started with Maxwell, who did out of the velocity distribution, that was the first step, and then Boltzmann, Ludwig Boltzmann, who was, as I told you, so impressed that rest of his life he carried this paper of Maxwell with him, and he is the one. So, this is the chronology. He is the one who started very seriously introducing concepts of probability theory, which was enormously criticized, because those days everybody believed the mechanical law of motion will be able to explain everything. And Boltzmann introduced many things. One of them is the Boltzmann Boltzmann kinetic equation, where he tried to develop. So Maxwell gave these Maxwell, and then a little bit of Boltzmann was able to, this one, all these things came out from, then your P 1/3 mnc square, CV 3/2 RT, then expressions for viscosity that I forget, but something to do with density and other things, sigma cube. So all these things, huge number of things flew from this equation. So the beginning birth of kinetic theory of gases started with Maxwell, and that was also the start of the statistical mechanics. But Maxwell and Boltzmann could connect to thermodynamics, but at the same time get the expressions like this, which are transport properties. And as you know, they also, this approach also gave the universal gas constant, which ultimately also used by many people including Einstein to get the estimate of Avogadro number, one of the landmark of Einstein's 1905 paper. Boltzmann wanted to go beyond this ideal gas, collisionless ideal gas. He introduced then this binary collision and binary collision operator, which even today is used. But in the process, he had to introduce essentially many body distribution function, because the probability of a particle at R1 V1 colliding with a guy, another particle R2 V2, and then going off R1 prime V1 prime R2 prime V2 prime. This is a hugely complicated thing, because these are 3-dimensional vectors. So he made an approximation that if R1 V1 R2 V2 F, that is F2, that becomes F1 R1 V1 and F1 R2 V2. That is called the approximation of molecular chaos by and large, for which he was criticized. But then what came out of Boltzmann's rigorous work is the definition of entropy, S equal to K ln omega, and that ultimately lead to the very heavily used by Gibbs. Okay. So then around that time we had van der Waals, and as I told you last day, the van der Waals had this famous van der Waals equation of state, and which has this kind of unphysical shape, but P versus density, and Maxwell did the Maxwell tie line construction. This work and this work motivated the person across the Atlantic, Willard Gibbs, who made this important observation that he of course knew all of Boltzmann. He knew this, the difficulty Boltzmann suffered in order to do a Newtonian description. That means everything obeys laws of conservation, Newton's laws of mechanics, and then of course as I told you, we cannot even solve 3-body problem. Willard Gibbs then realized that there could be a time independent, because if we have to solve this Avogadro number, because we are interested in 1 cc at least or 2 cc, then those many molecules you cannot solve in 3-body and even spheres, and forget about water or acetonitrile. So he realized very early the time dependent approach of Boltzmann is not going to go very far if I am doing the equilibrium properties, because for equilibrium properties it should not be that difficult. After all, as I told you yesterday, that we have millions of glasses of water, they are all the same properties. Then he realized one very important thing which I forgot to tell last time. He realized that such a system of, I forgot the number of, there have a huge number of microscopic states, and if I have billions and billions of my glass half full of water, then each of them will be in different microscopic states. And since each of them in different microscopic state at any given instant and exploring other microscopic states, it makes sense to talk of a distribution. And distribution, that is why he introduced the concept of ensemble, which I will elaborate a little bit more, because these things are other than the book of Tolman, I have not seen anybody doing a really good job on describing these things. But Tolman of course goes a little old fashioned and goes different things. So then the Willett-Gibbs, we do not need anything beyond Willett-Gibbs as of now. Willett-Gibbs explained how to think of van der Waals, he explained the phase equilibrium, the famous book of thermodynamics of heterogeneous system, and they were extremely impressed. Maxwell, of course, Boltzmann was going his time dependent venture, and when Maxwell died at a very young age, the joke was Willett-Gibbs was unmarried, lived the Starling laboratory at Yale, and he used to, only thing he used to take is to journey from his home to the second floor. But of course, before that 3 years he spent in Europe, after that where he learned all these things. And when Maxwell died, then the joke at Yale was that there was only one man who understood Gibbs and he is dead. So, but he alone kind of went on doing and did many things. Okay. Now coming back. So, he introduced all them, these 3, 1, 2, 4 introduced the concept of probability. And now I will briefly go through, not wasting too much time, to what, and you know there are enormous number of jokes about probability theory and many poetries and poems about probability, and this is my favorite of Sherlock Holmes. So now I will go through, but before that let me tell that we have this is my favorite book. This is not the book I have in mind. I told my student to put this together, but an introduction to probability theory by Kai Lai Chung. It is famous in a mathematics department by KLC. So they have 2 KLC, KLC 1 introduction to that is a wonderful book which I studied when I took a course on probability theory, and this is the one absolutely fantastic which many help I got when I solved the barrierless chemical reaction, which is a really quite a significant and is a classic now. I could do that because I knew how to solve method of images, by method of images and repeated reflections, all this technique I knew that I could solve that. And this is another beautiful book which is an introduction. These, I think all of them are available free on the internet, but this is beautiful because it thinks of talks of probability, determinism, then probability and deterministic together, goes on deriving beautiful equations. So these are highly recommended. So these 3 books for the probability theory that I recommend to everybody. So this particular part of the lecture will be motivation I have already done, little bit more, then I will go through what is a random variable, how do we define sample space which is so important in when you do the statistical mechanics, then probability distribution and the conditional probability. This is extremely important because conditional probability is the one that goes over to become the radial distribution function. So this conditional probability you have heard and read in I think and Bayeson's theorem, things like that in your undergraduate in your class 12, but that is the same thing. We again and again we come. Then we will do central limit theorem. As the name says, mathematicians are not given to adjectives, not like chemists. We say everything very interesting. They hardly say anything interesting. They say it is trivial. Feynman has a wonderful joke about mathematicians. Okay. So, as I said, what is the motivation? Is that in statistical mechanics one is interested in large macroscopic systems with many degrees of freedom, not several degrees of freedom, many degrees of freedom. 1 cc of liquid water contains these many molecules and each has 9 degrees of freedom. So, we are dealing with huge number. So, if we want to have a Newtonian description of solving positions and momentum of each particle, not only that we won't be able to do it, even in computers we are doing about it now probably few thousand, even then we need the same concepts that we will be using. Also, if we have all those things, we have no need for that. It is not necessary to have all these huge when we have started doing that, we could hardly simulate few hundred water molecules or few hundred Leonard Jones. So, we are a little bit more elaborate in describing, but now computer simulation has come a long way. So now these are very important and very loaded statement, and that we no longer can afford and no longer it is realistic or practical to take a deterministic approach, which is the Newtonian approach. Instead, we have to go to probabilistic approach, which was already initiated by Maxwell, was the first thing who did the single particle distribution. Now, there is a very important point that comes now, that what the experimental observables that we do, for example, specific heat or the density, they are all averages over random variables. If you look, for example, the standard edit Castellan book, if you remember, has this nice picture that how to get the pressure of a liquid, and what Castellan did was that he had a colored thing, and then it is full of water. Now, so water up to this and then water up to this is a colored liquid. What is now given, that if you now with a microscope, the optical microscope, ordinary microscope do that we have in our undergraduate or laboratories, you will find that height is continuously fluctuating. So, there is nothing really a constant pressure, and the pressure that we mean is we do an average over that, and it is a time average. Okay. So, this is a very important point in understanding that experimental observables are themselves a random number, and of course, when you do spectroscopy you get a broad distribution, that because the probe, which say dye molecule, you put in a liquid and then this dye molecule faces okay, when you put a dye molecule say 0.1 molar or 0.01 molar, so there is a 10 to the power 20 dye molecules, each of them facing a different environment. So, what we see in spectroscopy is an average again over all these molecules. Now, I will quickly go through something, I am just using this slide, I do not need to use that, but it is a little bit, it saves time and it is a little bit more precise. So, now we have to think, when I start discussing the going towards the statistical mechanics. So, we have till now we have argued that we give out the deterministic approach of Newtonian dynamics, Newtonian approach, and we are trying to go to a probabilistic approach, and the reason is that a deterministic approach is not feasible, B, that this should be the matter of choice, the probabilistic approach, and as I said they are all fluctuating. So, then the central quantity in statistical mechanics is a random variable x. For example, H here is a random variable. Energy of a system in environment or in equilibrium with a bath is a random system. So, is a random variable means we do not know and we will never know the exact instantaneous value of this quantity, but we know its average, we will know its second moment, if necessary we will know its fourth moment, but this quantity is a central quantity in our description of statistical mechanics. For example, you now realize that this random variable or set of random variable, I want a liquid and position of a water molecule in a liquid, then it will a position r orientation omega 1, then I would like to know another how far another water molecule with orientation omega 2 at position r2. So, in statistical mechanics, in chemistry, physics, all the time whether doing a conductivity, all the time we are talking with this quantity. So, this is a very general thing, x can take the quantity of our interest. Some examples of random variable, when you throw a die, random variable, this is a number of one, okay. So, possible outcomes are this, there is 1 or 6, each of them with 1 over 6. Similarly, our so this is the die and this is the coin where each side head or tail will be half. Now, there are some things which immediately comes to our things, like the way we do random walk, left or right, if one dimension is like throwing of a die. So, distance travelled by different walkers of a given time interval, instantaneous pressure of a liquid, as I said, number of nearest neighbor in a liquid, spherical molecules, it is anywhere between 9 and 13. So, these are very important quantities. You want to describe a random walk, you want to describe a walker, how far it is moving, how fast it is moving, which is diffusion, you want the pressure, everywhere we are doing with this kind of random, which is the same as essentially throwing of a die or the coin. So, random variable then, let me summarize, is a quantity of interest which can take a number of values which are not predetermined, but which follows a distribution as we will go through. Now, the collection of all the outcomes of the experiment is the sample space. This is very important. So, when we do in statistical mechanics, we integrate over some dx or something, we integrate over all the possible values, and all the possible values together define the sample space. Okay, like sample space of a coin tossed is head or tail is 2, then you got twice, the sample space become 4 because it can be head, head, tail. Same thing, coin tossed, this is the then the total weight of the sample space. Similarly, dice, if we throw many times, then we have, if twice, we have the 36 possibilities. So, then sample space which you have done in your school, like Venn diagram and similar things, it's just the collection of possible events. We need to know the collection of all the events because we would need to know the total sample space in order to define probability of a given event. So, we need all the events to know. Once we have all the events, then now we can say, okay, if I have a value that the probability that a variable has value in a continuous case between x and x plus dx px. Now, in a discrete it is easy, as we say in a die it will be 1 over 6, that what is the probability that it has value 1? It is 1 over 6. In a continuum you need the measure between x and dx. If it is a uniform distribution, then it will be the length dx by the total L, that will be, and it will be normalized because you integrate, you get dx equal to L. So, these are fairly trivial things, straightforward things, but one it gets a little bit more difficult more later. We describe the probability and outcome to a value between x and dx by px dx. This is normalized, so that it has to be somewhere, and that is now again the distribution. It will be, you can do minus L to plus L. There are many examples of that, as I told you. Very first one was given by Maxwell, and you have to realize that it came from nowhere. That means at that time nobody in 1850 or 60, nobody talked of probability distribution except mathematicians, but they are not applied to physics or chemistry. So, this was done by A, and he derived it, and the derivation is you have done in your undergraduate textbook, how you get this particular form. This is normalized because in 1D, for example, it have velocity can go to minus infinity to plus infinity, and this is normalization constant. This average velocity we know will go to 0, but then you have v square, which gives the width, which again is related to temperature, and the derivation of many things of kinetic theory of gases, almost everything in the elementary kinetic theory of gases flows from this equation.